Okay, good morning, everybody. How are you guys? I hope you are doing better now after the winter storm that hit Houston and the Texas area last week. I hope your power and water are back up now. Yeah, how are you doing, guys? I know it's the last few days are hard on everyone. But did you had by any chance were you able to take a look at some materials for test number two? Because I guess test number two was moved until the weekend. So now we'll spend the week trying to prepare for that, getting back into shape because I assume that you were not able to do any type of math in the last week. So yeah, we'll try to get back into shape in preparation for test number two. And for that, I prepared the worksheets 5 and 6. They are already up on my website. So, but basically, these are just the exercises from the textbook for sections 7.6 and 7.7. 7.6 is about separable differential equations and exponential growth and decay, while worksheet number 6 is about improper integrals. So I guess a couple of you guys mentioned you're having troubles about setting up or working with a model for exponential growth and decay. That's fine. We'll look into that. Let me see Christina's question. Oh yeah, I'll go over that, Christina. So yeah. Oh, can you guys check if you are if you're muted? Let's see if I can do that for everybody. Okay, so all right, so let's get going. But if you have some specific questions, just send them into the chat. Okay, so let's see. So or maybe you guys are a bit wondering why are we talking about exponential growth and decay again? Where in fact we're doing calculus and it's a little bit off topic. So let's see why. Because we're supposed to look at some applications of integrals, and one application of integrals is in solving separable differential equations. And one good example of a separable differential equation would be that equation that results into our exponential growth and decay model. But let's start with separable differential equations. What do we mean when we say differential equations? Well, we mean when we say differential equation, it's an equation that involves the derivative. So this is an equation involving derivatives. And one peculiar thing about differential equations is that we are not just solving for a number that satisfies the equation, but we're looking for functions. So the solution to differential equations, usually it's abbreviated as DE, are functions. So the final answer here would be functions. What are the functions that can be plugged into the differential equation that will make the equation true, right? So, okay. And then separability means simply you can put, if your differential equation involves two variables, you can separate them into the two sides of the equation. All that involves one of the variables will be on the left-hand side, and all those with the other variable will be on the right-hand side. And as I mentioned earlier, a nice example of a separable differential equation is this: dp over dt equals kp, right? So here the variables are p and t, but p is a function of t. So here, first it's a differential equation because it has the derivative dp over dt, right? So and then here we are solving for functions p of the variable t that satisfies the equation. So basically, we are looking for all those functions whose derivative with respect to t is equal to k times the function itself. So that's from an abstract or theoretical point of view. Be useful in several applications. Why? Because if you read it from an applied perspective, you see that the left-hand side is dp over dt, but basically that's the rate at which time, right? So dp over dt is basically the rate of change with respect to time. And the right-hand side is k times p. So basically that's a constant k times the current function value. So basically this equation is or just tells us that the rate at which p changes is proportional to the value of p. So here k is a constant. Right? An example of a function that is modeled in this way would be population. And that's why I use the variable p here for the function, because the rate at which population changes is proportional to the population itself. Meaning, if you have 10 persons in your population, then the rate of change will be smaller compared to a population with 100 persons, right? Because the more persons are there is in a population, then the faster would be the rate of change. Other typical examples would be on investments that are compounded continuously and so on. So those are some examples. But let's look at it from an abstract point of view first. So let's try to solve this differential equation. What are the functions p that satisfy this equation? Well, the first thing is to separate the variables. So not all differential equations are separable. So in this chapter of Cal 2, we are just concerned with separable differential equations. A more advanced course in math is required to solve other types of differential equations. So let's stick to the separable ones. So you see here that I can multiply both sides by dt, because my goal is all those with the p will be on the left-hand side and all those without would be on the right-hand side. So I multiply both sides by dt, and then I have a p on the right-hand side. So what I'll do is to divide both sides by p. So basically I'll have dp over p equals k dt. And this is the separated form of the differential equation, because all those with the p are on the left-hand side and all those involving the variable t would be on the right-hand side. So the two variables are on separate sides of the equation. Why do I want to separate them? Well, because if you'll be able to separate the variables, then you can simply integrate both sides of the equation. Because for now, all we can do is to integrate a function that is explicitly written in terms of a single variable, right? So that's why separation of the variables is a crucial step in solving separable differential equations, right? And then now we're ready to integrate. I guess it's easier to integrate the right-hand side. It's k dt, so the derivative would be kt plus an arbitrary constant. Let's call it c2, right? And then on the left-hand side, we have dp over p. Hopefully you still remember the integral of 1 over p with respect to p. We cannot use the power rule, but this is just the natural log of p, or the natural log of the absolute value of p, plus an arbitrary constant c1. Okay. And then I can subtract c1 from both sides. So I'll get this kt plus c2 minus c1. But look at c2 and c1. c2 and c1 are arbitrary constants. They stand for random constants, right? If you take the difference of two random constants, you get another random constant or another arbitrary constant. So that's why it's typical whenever taking the integral of both sides of an equation, we just put an arbitrary constant on one side. And that arbitrary constant c stands for the difference of the arbitrary constants from the left side and from the right side. Okay. So when I'm solving differential equations later, I'll just put one arbitrary constant on one side of the equation after the integration. The reason why I can do that because both sides will have their own arbitrary constants, but when I take the difference of those arbitrary constants, what I get back is another arbitrary constant, right? So just to save on the variables used on the problem, okay? Now we want to solve for the function p, right? That's the goal of this solving differential equations. Find the function p of the variable t that satisfies the equation. So here I can raise both sides to e because the function we're looking for is inside a natural log. So I'll use both sides as an exponents to e, right? Just to free up the variable p from the left-hand side, because here I can use the fact that the natural exponential function is the inverse of the natural logarithmic function. So basically, they will cancel each other out, leaving us with the absolute value p equals e to the kt, and then I'll just write it as e to the c using loss of exponents. Remember, when multiplying two powers of the same base, then you simply add their exponents, right? So, but here I'll assume that p is positive just to get rid of the absolute value symbol. So I'll have a p over here equals e to the kt, and then e to the c. Well, what can we say about that? Well, c is an arbitrary constant. If you use that as an exponent to e, we get another arbitrary constant, right? And let me call that arbitrary constant here p sub 0, okay, where p sub 0 equals e to the c. And this is basically the solution to the differential equation. This is a function of t equal to p sub 0 e to the kt. And this is the familiar exponential growth or decay model that you have seen in algebra or pre-calculus classes. So, but yeah, that's where this was derived. So any quantity that changes proportional to the amount of material present is modeled by this equation, the exponential growth or decay model. It's an exponential growth model if k is positive, and it's an exponential decay model if k is negative. All right. Right. Why do you think, guys, I used the variable p sub 0 for that arbitrary constant e to the c? Do you guys remember how p sub 0 was interpreted? Anybody?
The initial value or something, like the initial of something?
Yeah, that's correct, Fatuma. P sub 0 is the initial value. That's why we use P sub 0, meaning it's the value of the population or amount of material at time t equals 0. Right, so because if t equals 0, then P of 0 is equal to P sub 0 e to the k times 0. But that's just e to the 0, but e to the 0 is 1. That's why it's p sub 0. That's why we call it p sub 0, because it turns out that that constant is the initial value. Okay, yeah, Kevin, you're correct. That's the initial population. So basically, that's what I want you to remember for this model. P of t is basically the current value or the current value at time t. P sub 0 is the initial value. And k is the rate of growth or decay. Okay. Now let's look at how we can use this this model. Let's look at a couple of problems here. Usual example would be population dynamics. Let's see. I guess problem 28 is more interesting. Let's see. Okay, this problem tells us that in 1980, the world population was approximately 4.5 billion, and in the year 2000, it was approximately 6 billion. And assume that the world population at each time t increases at a rate proportional to the population at time t. measure t in years after 1980, and then there are 3 separate problems here. Well, if you look at the problem, look at this assumption. We were told to assume that the world population at each time t increases at a rate proportional to the population at time t, which I guess is a reasonable assumption. But for us, that means that, or that's the signal that we should use exponential growth or decay model, because the population is said to increase at a rate that is proportional to the current population. So basically, that statement there tells us that dp over dt, the rate at which the population changes, is proportional to the population, or to the current population. But again, remember that earlier we already solved this separable differential equations. We said that the solution here is p of t equals p sub 0 e to the kt for some constant k. So we know what would be the model. So we don't need to solve this differential equation over and over again. We can just rely on what we did earlier and remember that the model is like this. Now, what's the other information here? We were told that we need to measure t in years after 980. So that means the year 1980 would be our t equals 0. 1981 would be our t equals 1, and so on, right? That means p sub 0, the initial population, or the population at time 0, would be the population in 1980. And it is said in the problem that in 1980, the population is approximately 4.5 billion people, all right? So that would be our p sub 0. So our model now can be rewritten as p of t equals 4.5 billion e to the kt. That's the model we want to work with, okay? Now let's try to answer problem A. For problem A, we were supposed to give the constant, the growth constant k, for any given time t. Well, we need some information to solve for the value of k. And good enough, there's another info in the problem that we haven't used yet. It says that in the year 2000, the population is about 6 billion. So that means year 2000 corresponds to t equals 20, right? Because our t equals 0 is 1980. So that means from the problem, p of 20, the population at the year 2000 is said to be 6 billion. This is from the problem, right? But from the model, another way of looking at p of 20 is that it is 4.5 times 10 to the 9th e to the k times 20. How did I get that? Well, I got that from our model. Our model says that p of t for any value of t is 4.5 billion times e to the kt. So to find p of 20, I simply plug in t equals 20, and I get this expression for p of 20. Okay? Now we have two values for p of 20. For our model to be consistent, then these two guys should be equal to each other, right? So that means they are both representations for p of 20, so they should be equal to each other. So we have 4.5 times 10 to the 9th e to the 20k should be equal to 6 times 10 to the 9. Again, the reason, because they are both p of 20. And then the goal for problem A is to find k, or is to solve for k. So first thing, I can divide both sides by 4.5 billion. So I have 6 times 10 to the 9th. Then let me write 4.5 as 9 over 2 times 10 to the 9th. Well, the billions will cancel each other out. So this will just be what? This will just be 6 times 2 over 9. And then this is, I can cancel 3 here. So there would be a 2 left there. So this would be 4/3, right? So basically what we have is e to the 20k equals 4/3. Okay. And then we're solving for k. So if you remember, to free an exponent we need to take the natural log of both sides. Or actually, you can take the log, any logarithm of both. So doing so, I'll take the ln of both sides. So let me just show you all the steps here. But definitely you can skip some of the obvious ones, such as this one in your solutions. I'll use loss of logarithm. Remember, loss of logarithms tells us that if you have an exponent inside a log, that can come out as a coefficient, ln of 4/3. Okay. Oh, ln of e is just equal to 1. So we'll have 20k equals ln of 4/3. And then to find k, we simply divide both sides by 20. So that would be the growth factor, or the rate of the growth rate for the population. Okay. So this would be our answer for part A. And actually, this gives us another info. So the model now can be updated so that the model now reads 4.5 billion e to the ln of 4/3 over 20. That's the value for k times the time t. All right. Is that good so far? Actually, in my previous class, I just realized how nerdy I am back when I was in early high school, or just after grade 6 or something, when we learned exponential growth and decay. I went to some of my encyclopedia. I looked for some population data for countries, and I tried to forecast the population for those countries in 20 years' time using this model. And as a child, or as a kid back then, it was a big deal for me because um, um, at that particular point, for me, it was a big thing to be able to forecast what would be the population 10 or 20 years from that time. So yeah, as a kid, that's a big deal. And now I just realized how nerdy I am back then. Well, yeah, I just love numbers. I don't know if I'm good at math back then, but when I learned this, yeah, I just went to those almanacs, started computing the K values for these countries. I have 200 countries back then, and then I tried solving for these, right? So, but that's how powerful this tool is. This is just a basic thing, and yet this has a very nice application. So, yeah. Okay, enough of my nerdy side. So, is this clear? Let's try problem B. What is problem B? Okay, problem B is asking how long will it take for the population to reach 9 billion? To reach 9 billion, right? So that means we're looking for a time value here. So we need to find t, the number of years, so that p of t is equal to 9 billion. Okay? So we're looking for t such that this equation will be true. The population at that year is equal to 9 billion. But I can replace the the left-hand side by the model that we had defined earlier, right? So p of t is given by that model. So I'll just rewrite it down here. E to the ln of 4/3 over 20 times t equals 9 times 10 to the 9th. Okay. And then here we want to solve for t. So basically, I want t to be isolated on one side of the equation. So I can divide both sides by 4.5 billion. So I'll have this. Okay. And then since the variable t that we want to find a value of is in the exponent of e, again, I'll take the ln of both sides so that t will come down as a coefficient. Right? So we'll have ln of 4/3 over 20t times ln of e, right? Again, this is the crucial step applying loss of logarithms here. This exponent of e inside the log will come down as a coefficient. That's all that happened there. And that's the reason why I took the natural log of both sides. In theory, you could have taken the logarithm to any base of both sides. But it's more convenient to use ln because you'll be left with an ln of e, and ln of e is just equal to 1. So here we'll have ln of 4/3 over 20 times t equals ln 2. Then remember, we're solving for t. So basically here we'll have 20 ln 2 all over ln of 4/3. Okay. Whatever its value is. So in exams, homeworks, or quizzes, unless it's a multiple choice quiz, then you can leave your answers like this. Actually, I would encourage you to leave your answers like this for written homeworks or for exams, because you're not supposed to use calculators to find the decimal values. So yeah, this would be a perfectly fine final answer, whatever the value of t is. All right. Everything's clear? So you see here, it's just interpreting all parts of the model. The good thing about this model is that it entails just a few number of things, right? The model is p of t equals p sub 0 e to the kt. P sub 0 is whatever initial info is given in the problem. K is the rate of change. Usually you will be asked to derive them. You'll be lucky if that will be given in the problem. And t is the number of years, or usually it's the time, the time variable. Okay. Okay, let's see problem C. Problem C, the world population for 2010 was reported to be 6.9 billion. What population does the formula in A predict for the year 2010? And how close it is to the reported population for 2010. Okay. Now, how do we find the population for 2010? Well, first you note that 2010, corresponds to t equals 30, right? Because our t equals 0 is 1980. So the population, or our prediction for the population using our model for the 2010 is p of 30, right? You simply use t equals 30. So that would be p sub 0, which is 4.5 billion from the problem. We saw that earlier. E to the k, but we know k is ln of 4/3 over 20 times t. And that's it. This is the predicted population for 2010. So, or you can just carry out some of the multiplications here. You'll have e to the 3/2 of ln 4/3. If you use a calculator, I guess this would be 6.9282 times 10 to the 9th. So that's 6.93 billion, which is pretty close to the reported population in 2010, which is 6.9 billion. Okay. You're being quiet again, or too quiet again. Is that clear?
Yeah. All good.
Okay, thank you. Yeah, let's see Christina's question. Christina's question is about half-life, which is another nice application of population growth and decay. And I guess usually these are the type of questions you have in algebra or in pre-calculus. Okay, let me answer exactly Christina's question here. That's problem 21, I guess. So if you're majoring in chemistry, then this would be something familiar to you. So it says here that the half-life of radium-226 is 1620 years. I hope I'm not mistaken, but I think radioactive materials decay. So that means after some time, you will have less amount of sample for these radioactive materials. And the term half-life is used to describe the number of years before half of the sample will be gone. So half-life, this is the amount of time before half of the sample will be gone. So if you have 100 grams, say, of radium right now, then after 1620 years, you will just have 50 grams left. And these materials exhibit exponential decay, right? It's decaying because, yeah, the amount of material decreases with respect to time. So for this type of problems, we expect K to be negative, and the decay rate of the material will be proportional to the amount of material that is present. So the more material present, the faster the decay would be, because the higher the decay rate would be, right? So basically here, we want to answer two problems. The first problem wants us to predict how much of the radium will be present after 500 years. So before answering parts A or B, we need to have a model for the behavior of radium, or the amount of radium present in a particular time, t, right? So let's use the concept of half-life to derive it. We know that the general model would be P of t, amount of material at time t, is equal to the initial amount P sub 0 e to the kt. This is the general model. Whenever we know that the rate at which the function changes is proportional to the function itself. It's a decay problem, so we expect k to be less than 0. Okay. Now, how do we find k and p sub 0 here? Well, actually, we can leave p sub 0 as a p sub 0 and find its value later. But the more crucial here is finding k, right? We need to find k, and for that, we need some info from the problem. Well, it's a one-sentence problem, so basically it tells us that the half-life is 1620 years. And remember how we defined half-life. We said that the half-life is the amount of time before half of the sample will be gone. So that means in 1620 years, right? Because that's the half-life, and it will take 1,620 years for half of the radium to be gone. So that means at P of 1620, only half of the original amount will remain. So I'll have half of the original amount, but we said that the original amount is P sub 0. All right. So this is basically from the half-life info. In 1620 years, only half of the initial amount will be present. That's why we got this, right? But another way of looking at P of 1620 is coming from the model. So the model says that P sub 0 e to the k, which is unknown, but we know that t is 1620. So this is from the model. But these two guys refer to the same thing. These two expressions pertain to P of 1620. So for consistency, the two right-hand sides should be equal to each other. So we impose that P sub 0 e to the 1620k should be equal to 1/2 P sub 0, right? Again, because they represent the same thing. They represent the same quantity P of 1620. And now let's solve for k. Well, I can divide both sides by P sub 0. And we'll just have 1/2 on the right-hand side. And that's why P sub 0 is not important for half-life problems, because when you are solving for k, P sub 0 will be canceled from both sides. Okay. And then we need to free k out of the exponent. So I take the natural log of both sides. Okay. And then the exponent will be going down as a coefficient. Supposedly, you'll have ln e here, but ln of e is just equal to 1. So that will be gone in the next step, right? So, and then I will divide both sides by 1620. So we'll get k equals ln of 1/2 over 1620. Okay, and this is the rate of decay. Well, remember that I mentioned that we are expecting k to be negative. If you will use a calculator, you will see that ln of 1/2 over 1620 is indeed negative. But an easier way to find it out is that whenever you have a fraction, always give you a negative value. So since 1/2 is a fraction, it's a number less than 1. Inside the ln, it gives out a negative number. Negative number divided by 1620, that would be a negative number. Okay, so that's why for certain k is negative, hence we have exponential decay as we expected. Okay, So therefore, the model is this now. Initial time or initial value, e to the ln of 1/2 over 1620 times the time value. So this would be our model for the decay of radium-226. Okay? And I guess now we can answer part A. Part A tells us what? It tells us to compute how many or how much of the radium will be left after 500 years if originally 100 grams of it is present. Okay, so that means here we take t equals 0 to be the current time. So that P sub 0, which is the amount of material at time 0, is equal to 100 grams from the problem, right? So it says that at this particular moment, there's 100 grams of the radium present. And we're looking for how much of that radium will be present after 500 years from now. So 500 years from now is T equals 500. Okay. So that means we're looking for P of 500. And P of 500, let me just double check the problem. Yeah, we're looking for 500 years. Okay, so this will just be P sub 0, which is 100 grams, times e to the ln of 1/2 over 1620 times 500. And that would be it. And this would be the number of grams present. Okay. So this would be easier because you will not be expected to simplify this if it's a written homework or if it's in the exam. You can leave your answers like this, right? Or if you want to do some of the arithmetic calculations, you can write it as what? 500 over 1620. I'll have 50 over 162. I can divide top and bottom by 2, so I'll have 25 versus 81. ln of 1/2 grams. Right? But I'm perfectly fine with this as final answer. Right? So because all that it takes to get to the next line will just be simple arithmetic. Okay, and then let's try question B. For question B, how long will it take for the sample to be reduced to 25 grams? So we want to find T. Okay, so we need to find T such that the amount of radium at that time T is equal to 25 grams, right? So that's what we're looking for. Okay. Oh, but we know that P of T is given by 100 e to the ln of 1/2 over 1620 times T, right? That's our P of T model. And we want this to be equal to 25. And then we want to solve for T. Well, we'll have e to the ln of, I'll divide both sides by 100. So I'll have e to the ln 1/2 over 1620t equals 25 over 100, that's 1/4. And then I want to free t out of the exponent, so I take the natural log of both sides. If you take the natural log of both sides, you'll get ln of 1/2 over 1620t times ln e equals 1/4. But we all know that ln of e is just 1. So basically here we'll have ln 1/2 over 1620t equals, sorry, this should be ln of 1/4. Because remember, we took the natural log of both sides. So this would be equals ln of 1/4. And then let's do the algebra. To find t. So t would be ln of 1/4 all over ln of 1/2 over 1620. or basically this is t equals 1620 ln of 1/4 over ln of 1/2. Okay. So again, if it's not a multiple choice problem, then you can leave your answer like this, right? Because you are not supposed, or you are not expected to use calculators. But I guess here it is approximately 3,240. So that means it takes that amount of time for only 25 grams of the radium to be left. Okay. Okay, that's good to know, Kevin. How about the others? Are you feeling better now about exponential growth and decay? You see that it is like any problem solving strategy. You should know the model, right? So our model in this case happens to be I would say simple. It's p of t equals p sub 0 e to the kt. And it's just interpreting all those numbers given in the problem, putting them little by little into the equation so that we will have an explicit model, meaning you have a model with only the variable t to be unknown. And then you can just play around with that model based on what the problem is asking for or what are the given information. Okay, no other questions? We still have some time, so I would like to, if you don't have any other questions about exponential growth and decay, I would like to solve some separable differential equations, because if I remember it right, you were not able to discuss this in the lecture, but instead you were told to watch a video about it. So I don't know if you got the chance to watch the videos about it. But I guess it would be worthy to, or it would be worthwhile to look at at least a couple such problems, right? So if you look at the top of the worksheet, it has problems 1 to 12. All of these are differential equations because they involve the derivatives, right? And again, our goal here is not to simply look for a number y that satisfies this equation, but we're looking for functions y that satisfy this equation. Okay, let's see. Let's try some simple ones. Perhaps let's start with yeah, let's try with problem 1. Okay, so let's see. For problem 1, of course, we have seen an example of solving separable differential equations. That's what we did at the beginning of this session, right? When we solved that differential equation wherein the rate of change is proportional to the amount of material present, right? So these are more general examples, of separable differential equations. So let me just copy it from my other screen, okay? So let's try problem 1. It says that y prime is equal to x times y, and y of 0 is equal to 5. Well, this is the differential equation, and this is what we call an initial value. So here we want to find a function whose derivative is x times y, and the value of y at 0 is equal to 5. So let's see how to do this. The first step is to write the derivative in terms of the Leibniz notation. I mean, you have y prime. We know that y prime is just another way of writing dy over dx. And I prefer using dy over dx at this point because I want to separate the variables. So dy over dx gives me a way how to, instead of looking at the derivative, but instead of working with derivatives, we will work with individual differentials, okay? So next, I want to separate the variables. So in this case, I want all those with a y to be on the left side, all those with an x to the right side. So what I can do is to divide both sides, to multiply both sides by dx. So I'll have dy left here, and then I'll copy the x here, and I'll have a dx here. Supposedly there's a y, but I want y to be on the other side. So what I'll do is to divide both sides by y. And we have this. So this is the separated form for the differential equation, right? And this is extremely helpful because to find y, I can simply integrate both sides of the equation, right? And when I integrate, the integral of dy over y is ln of the absolute value of y equals x squared over 2 plus the arbitrary constant c, right? Remember, when you are integrating, both integrals were supposed to have an arbitrary constant c1 and c2, but I can put the arbitrary constant from the left, transfer it to the other side, and I'll have c2 minus c1 as what we have seen before, but c2 minus c1 is another arbitrary constant. Again, that's why it's customary to just put an arbitrary constant to one side of the equation. Okay? And then now we want to solve for y. So we simply raise both sides, raise e to both sides. So I'll have e to the ln absolute value of y equals e to the x squared over 2 plus c, right? So this would be absolute value of y equals e to the x squared over 2 times e to the c, right? Loss of exponents. But here I can write e to the c again as just an arbitrary constant. Let's call it a e to the x squared over 2. So therefore, what we see here is that we have an absolute value of y equals a times e to the x squared over 2. But this is not, this is the solution to the differential equation, because the solution to a differential equation is not unique, okay? So we can have several solutions. For instance, in this problem, in this differential equation, you can have different solutions if you put in a random value for capital A. So you can say capital A is equal to 1. Capital A is equal to 7. Capital A would be equal to 10. They all give the same as, they all give solutions to the differential equation. So the solution is not unique. But remember in the problem, we have an initial condition here. We want that the value of y when x is equal to 0 is equal to 5. So if you have an initial condition, that can make the solution unique, right? So in particular, so since we want y of 0 is equal to 5, then that means when you plug in x equals 0 into the solution, you get 5. Y equals 5. So that means we'll have 5 equals a e to the 0 squared over 2, right? So I simply plug in x equals 0. So I get a e to the 0 squared over 2. And that should be equal to 5 according to the initial condition, right? But e to the 0 squared over 2 is just 1. So I'll have a. So that means a is equal to 5. So therefore, the solution to the differential equation is absolute value of y is equal to 5 e to the x squared over 2. Okay. Is that good? Let's have another quick one. This is problem 4. Hopefully I can finish it in a minute or two. Y prime is equal to e to the x plus y. Again, our goal is to separate the variables, right? So y prime, I'll rewrite it as dy over dx in preparation for the separation. And then the right-hand side can be written as e to the x times e to the y, loss of exponents. And then do the separation. Well, I will divide both sides by e to the y and multiply both sides by dx so that I'll have dy over e to the y equals e to the x dx. Okay? And then I'll integrate both sides. I'll have e to the negative y dy equals integral of e to the x dx. So I guess we'll have a little bit of a problem on the left-hand side. So I'll use u sub in the left-hand side. So I'll let u to be equal to negative y. That means du is negative dy, right? So the equation, the integral on the left can be rewritten as negative integral of e to the u du equals integral of e to the x dx. And this is simply negative e to the u equals e to the x plus an arbitrary constant c. Okay. And then I'll revert to the original variable. I'll have negative e to the negative y equals e to the x plus the arbitrary constant c. Okay. Now, I guess this is an acceptable final solution because all the derivatives and integrals are gone, though we were not, or we did not write the equation, the function y explicitly in terms of x. My only hesitation to do so is that it would be a little bit complicated because there should be some absolute values involved. But essentially, you can leave it like this because there are no derivatives or integrals left. So this is the relation. And then problem number 4 doesn't have any initial condition. So that means there are infinitely many solutions here. In fact, you can generate different solutions by picking out different values for C. Again, that's because there's no initial condition imposed on the function. So all functions of the form this serve as solutions to your differential equation. Okay? Is that good, guys? Okay, so you want to be quiet. Okay, that's fine. If you are still trying to digest these things, that's fine. So okay, so what we'll do next time, probably I'll cover a couple more separable differential equations at the beginning of the lab on Wednesday, and after that, let's jump to improper integrals. Okay. Okay, so and then plus if you have some questions about the practice test or quizzes, just let me know on Wednesday so we can discuss them. Christina has a question for 22A. What do you mean? 22A, let's see. You have a different problem. So 22A. So for your 22A, yeah, so for 22A, you'll use P of negative 200. Because Christina, for 22A, you were told to find the mass 200 years ago. And if you will set t equals 0 to be the time today, then 200 years ago will correspond to negative 200. So that means for 22A, you'll be looking at p of negative 200. Right? Mm-hmm. So yeah, it would be helpful if you write those details down. So for instance, you say that I'll set today is t equals 0. And then that means it's easier to realize that 200 years ago would be t equals negative 200. Okay, and that's what you need to plug in into your formula in order to get the amount of material to present 200 years ago. Okay. All right. So, okay, no other questions? And if not, then let's call it a day. Thank you for coming today. Hopefully you stay safe you stay safe. Hopefully you're not affected anymore by any power or water outages. But yeah, have a good one, everybody, and see you again on Wednesday. Before I leave, Kevin, if it's asking for how long till we get the sample reduced 75%. Yeah, that's right, Kevin. So if you're looking for the amount of time it takes for the sample to be reduced by 75%, then you will take P of t equals 25% of P sub 0. Because you assume that, yeah, 25% of 100, yeah. Mm-hmm. Okay, your P sub 0 is 100. All right. Okay, goodbye, guys. See you again on Wednesday.